So all we are talking about GigE Vision and 100 gigabit this afternoon. A few things might be repeated, but a few other things are reflected from a different perspective in my presentation. So what I want to do is first to give an idea why we have the motivation to introduce a new major version of GigE Vision. We have heard about a few arguments, but I'll summarize that. Then 25G, 100G for GigE Vision. Short recap, what is GigE Vision and what are the technical backgrounds of Remote DMA Rocky V2 for GigE Vision? A few aspects we heard, but not all. And I close with the specification and implementation status, implementation from our point of view, and technical requirements for manufacturer of machine vision components. What is the background here? What has to be what has to be seen here. About sensor to image, we are in the market since 1989 as a specialist for custom specific machine vision components. We are since almost 20 years IP vendor to build machine vision components. So we support you in doing your own applications for GigE Vision, for USB Vision, for Core Express, but also for sensor interfaces like Sony IMX sensors or MIPI interfaces. Since 2017, we are part of Euresys, which is also a specialist for image acquisition and image processing tools. Okay, going to the motivation. The standardized machine vision interfaces we have today work well up to 40 gigabit per second, CXP12 by 4, for example, or others. But sensor manufacturers have roadmap up to 800 gigabit per second, so you see there's a big gap in between. 100 gigabit sensors are already in the market, and you have heard there are products in the market for that. Yes. GigE Vision is a well-established interface standard, but as we see in the next slide, we have to make it fit for these higher data rates. GigE Vision itself, as mentioned before, released in 2006. Current version is 2.2 with a lot of improvements to support modern sensors with new pixel formats, multi-component data, 3D or something like that, synchronization of several cameras, higher data rates. And this is ongoing, these improvements. GigE Vision itself, from the beginning, is a UDP-based protocol for exchanging control information using the control channel, streaming data using the streaming channel, and it requires GenICam as this XML file and standard feature naming convention to work easily with applications. This is the state today. Why do we need, or why the technical committee of GigE Vision thinks to need a new version of GigE Vision 3.0? With the existing GigE Vision streaming protocol, there are streaming issues, especially as higher data rates. We have a poor receiver performance with standard operating network stacks, which means high CPU load, high interrupt rate, multiple buffer copy, and at the end, this leads to packet loss. And this is, of course, nothing we want to have. We have some sort of reliability achieved using an application level packet resend, but you see that in the block diagram. Camera is sending data, the application on the very right side, GigE Vision application detects a missing packet, then it resends or asks for resending packets. So that leads into a large packet resend loop, which means large latency with strong impact on the performance, especially at high data rates. At 1G, it's fine, but at 10G, it's already at the limits. And it also requires a large stream data buffer required on device side. There are several improvements what could be done for that protocol. low-level kernel filter drivers bypassing the operating system network stack is quite standard. This is a kind of partial improvement that helps up to 5 to 10 gigabit per second, but this is not really scalable. So for higher data rates, that does not really work. Offloading the reception to specialized hardware, custom developed frame grabbers, FPGA or ASIC based. There are a few in the market. Proprietary features of selected NICs, header data split, and scatter-gather DMA. Yes, that's possible. But both lack the main GigE Vision advantage, standard hardware and standard software components. So the final option would be replace the UDP GV or UDP-based GVSP protocol by a more efficient standard transport protocol. And yeah, almost 10 years, the technical committee discussed about that and checked that and yeah, evaluated remote DMA approaches. And yeah, here we had and have two competing standards, iWarp and Rocky or Rocky V2. Meanwhile, we can say that Rocky V2 is the winner, and this is supported by all major NIC vendors for a little bit higher class NICs, unlike iWarp. To give you an expression or impression about the data rate, what we want to achieve and what is possible today with the GVSP protocol today, UDP based GVSP protocol, 5G, 10G. So this is the limit, could be increased using by vendor specific filter drivers. Sometime a time TCP was in the discussion, but at the end, it turned out that this will not really bring an improvement. So maybe up to 25G, but not more. In remote DMA, this makes really the door open to 25G, 100G, and even 400G. This is the goal of the change of that transport protocol. What is Rocky V2? Rocky V2 is the abbreviation for Remote DMA over Converged Ethernet version 2. This is, as previous mentioned, not a new development. It's specified in the InfiniBand architecture specification. And Rocky V2 specifies that protocol InfiniBand on the Ethernet infrastructure. So Ethernet and still UDP IP packets. But within that packets, we have some enhancements, so we do not have the same disadvantages like with the existing GVSP protocol. It offers hardware offloaded, zero copy data transfer, and that brings high performance, low latency, high efficiency, reliability, and data consistency. The block diagram, you see that a little bit on the left side. We have the situation today, especially the target side is the interesting one. We have the NIC, we have the network driver, we have a transport call driver, sockets, applications, so a lot of buffers which have to be filled, and that costs a lot of performance. Using Rocky or Rocky V2, we have this Rocky enabled networking card, and together with the driver, it's possible to directly copy the payload to the application buffer. So it's not longer needed to play with filter drivers or to make special hacks to get the data to the application. The highlights: it's an industry-proven standard. It's deployed in data centers and high-performance computing application for years, so it's nothing new. Mirko mentioned that as well. It's high performance, high efficiency. It's a fully hardware offloaded protocol, so the reception of the data can be directly done by the network cards and do not need the interaction of the operating system. The kernel is bypassed directly with a direct memory access, so no kernel and CPU influence is influenced. We have a guaranteed packet delivery. It's an in-order packet delivery and buffer delivery, and one big advantage also, this GigE Vision packet resend is not needed anymore. Still, we have a low latency protocol. It's still UDP based, so it's still simple to implement, and optional retransmission is directly implemented in hardware, not like in application level, what we had with the packet resend. It's directly implemented in hardware, what minimizes the delay. What is the basic concept of RoCEv2 streaming? It's organized in so-called queue pairs. This is a pair of related queues for transmit and receive buffers. They are connected to each other and on application level, so that the camera knows where to stream the data and the receiver knows where to copy the data at the end. So this is done in a double-side approach for sending and receiving data. So the receiver, the host, allocates and enqueues empty buffers for the receive process, and the transmitter, the camera, enqueues data buffers to be sent using the send command. About hardware support, RoCEv2 is a fully routable protocol based on Ethernet and UDP IP. So natively, it's supported by any Ethernet switch and router. So Mirko, you mentioned you need some RoCEv2 enabled switches. Might be that this is for the highest end, but for a 10G application or so, you can use your standard Ethernet switch and router, so no special hardware is required. RoCEv2 is natively supported by most of today's higher-end NICs. These are typically 10, 25 gigabit cards with optical fiber, or 100 gigabit cards. So NVIDIA Mellanox chipsets support RoCEv2. This is a little bit the gold standard, best performance and compatibility. Newer Intel NICs and chipsets support both the not used IWAP, but also the RoCE protocol. Marvel chipsets support RoCE, and also Broadcom has chipsets and network cards supporting RoCE and RoCEv2. You have to be a little bit careful about driver support. Not all network cards support both Windows and Linux, or Linux is always supported, but Windows not in all versions. So here a little bit careful. Impact on a device design. So we are doing IP cores and reference designs to implement GigE Vision 2.x and now 3.x. And of course, we compared the size, what is needed to implement such a design. From the FPGA resources, the logic, FPGA logic, this is more or less comparable. There's not much difference. But we need a little bit more local memory buffer. But on the other hand side, we do not need external frame buffer anymore. So you see that a little bit in the bar graph on the right side. DRAM, this is local memory. This is larger, but flip-flops and lookup tables. So these native elements you need to program FPGAs, they are almost the same. On the data ring buffering, GVSP packet resend needs a large external memory, and especially at higher data rate, this gets more and more complicated to get the data rate over to the network. This is solved with using RoCEv2, because here we have a reliable connection. So that means we can expect that all packets are delivered, and for that, we only need an internal packet buffer, no external buffer anymore. What about the specification? The RDMA proposal is accepted and frozen. So this was done the last IVSM. The GigE Vision 3.0 specification draft is currently in progress to be written. And that specification release candidate should be then out after the next IVSM in spring 2025. The official release is planned for the second half of 2025. Let's see. But as Mirko already said, you can start working with that. Especially the RDMA proposal is frozen, so this is fixed. We know what we want to implement and what has to be implemented, so it's possible to start today. From our point of view, from sensor to image point of view and IP core side, we have a working prototype. So that's a GigE Vision device IP core according to the GigE Vision 3.0 specification draft, what is currently available. Rocky V2 streaming at 25 gigabits is using the reliable connection send transport function is implemented. GigE Vision 3.0 also requires GenDC payload type in the GigE Vision or in the Rocky V2 streaming mode. This is implemented. On software side, we have support in the Euresys eGrabber GigE Link software. We demonstrated that in the last Vision show, and commercial IP is available beginning of next year. Finally, technical requirements on device side, cameras. FPGA transceivers are the key feature for modern vision systems and also for GigE Vision systems. So you need 10G transceivers for 10G GigE Vision systems and 25G transceivers for 25G or 100G GigE Vision systems. There's additional IP needed for PCS PMA, but this is typically required by provided by the FPGA manufacturer. On host side, you can choose between different network cards, network vendors. It is required that they support the Rocky V2 protocol. To sum that up, GigE Vision streaming protocol as of today is not ready for data rates above 10 gigabit per second. The GigE Vision technical committee decided to use a subset of the Rocky V2 protocol, especially the reliable connection send transport function as a low-level transport protocol for Ethernet streaming at 25 gigabit per second and more. GigE Vision 3.0 will include Rocky V2 as streaming protocol. And we as Sensor to Image have a first implementation of an FPGA IP core supporting the upcoming GigE Vision 3.0 standard. Okay, thank you.
Okay, thank you, Matthias. I have another question for Matthias Schachland. What is your roadmap to support GigE Vision 3 and 100G?
Yeah, I mentioned that we have a working prototype of a reference design for GigE Vision 3.0 in until Q1 2025. We want to implement several Q pairs, which is needed if you want to run the GenDC protocol or GenDC container in a more complex way, not just transferring a single image, but more concurrent images and so on. Then you need more Q pairs, and until mid of next year to integrate the 100G into the IP core.
And are there any other companies using RDMA in their vision products that you're aware of?
Yeah, we see it here. So yes, there are a few customers or companies using this RDMA technology. Yes.
Okay, thank you. I'm looking at the time. I think we have to come slowly to a close. Maybe one last question for everyone. If you would like to give a short answer, what do you see as the biggest benefit of GigE Vision 3.0 RDMA? Maybe Matthias, you can start.
The reliability for higher data width. We see the limitations with at around 10 gigabit with the current GigE Vision, and this is what we want to solve.
Okay, thank you. And I think with that, we will have to close our last session for today. I'd like to say thanks to all the speakers and of course the audience.